Hi everyone, and welcome to Datacom Lab 3. In this lab we're going to study TCP and UDP using wireshark. For this lab you'll need a number of documents that you'll find in eConestoga. You have the Datacom Lab 3 TCP UDP answers.doc, and this is similar to our last lab. It's the file that you're going to use to hand in when you put your answers to the questions from the lab manual. The lab manual has a number of questions. They may not be exactly the same as in this document, but anyway, they're very close, and you'll be able to determine what section each question is coming from. Along with the lab manual, there are a number of wireshark files. So these are capture files with the .cap extension, and these were already done. So there was an experiment. In this lab, you're going to see the description, or in the manual, you're going to see the description of the experiment that was used to produce a number of capture files. So there would be different situations for each of the capture files. Okay, and in the next slide, you're going to see a video walkthrough of this lab. Okay, so now that we are oriented, what we're going to do, we're going to take a look at the documents that we need. The documents include, okay, so here are the questions. Okay, so in this section, these are the questions, the document that you're gonna fill out. We have exercise 1 question, so this is part A. Okay, each section has a different point, and we'll talk about each of a different setup basically. Okay, so this is part A is when you have a remote server and there's no noise to create errors in the packets. Okay, so we're studying TCP, how TCP can be used for reliable transport, and if there's any errors, they'll be corrected. Okay, so we're gonna see that. And so in one of the experiments, there's later on you'll see that noise is introduced into the connection, and then we see how TCP can be used to deal with this problem. Okay, so there's part A. There's part B, where again we have a connection to a local server with no noise. This one was a remote server with no noise, and again there are associated capture files for each of these sections. Here is a diagram for the different setups, okay, and it tells you how each of the files, okay, how each of the files were produced, the setup for each of these files, okay, and that's in here. And again, these questions are related to the lab itself. So we have exercise 1, we have part A and part B with no noise, okay, and this just does your standard TCP connections. And then we have exercise 2 where we add noise and interference. Okay, and in exercise 2 we have some interference between the laptop and the desktop that are on the local network. Okay, so we'll talk about more of these details, and you'll see the different retransmissions basically. So these are capture files with different retransmissions is when there's error, right, in a packet that gets retransmitted. So we're going to look at different capture files. This has already been done for us, so we don't actually need to do anything on our local network to capture them. We are going to use wireshark to view these capture files. Okay, so that's basically it for this. We're going to keep this open. Okay, I will keep this one open. One thing, the things you need to download, again, once you download them, you're going to have the different the PowerPoint presentation. You're going to have this is what you're going to fill your answers in. You got your manual here, and then these are all of the capture files, okay, that are part of this this lab. All right, so let's lower that for a second, and what we want to do is open up our lab manual. Okay, so I'll put the lab manual here, put the questions here, and we can go through what's needed for each of them. Okay, so let's zoom out a little bit of this one. Okay, so look, this lab, there are 27 pages. There's quite a bit of reading to do to basically, I mean, all of this is to understand the setup that was done in order to produce these capture files. Okay, so you're going to download these files and put them in a folder. So this section here is just an overview of TCP, and you need to kind of know, how it works. We talked about this in class, but basically TCP is reliable and it reorders packets. And there's retransmission of lost packets. UDP does not have this. Okay, there's no in-order message delivery. There's no, error control, etc. Okay. So this is overview. The two exercises we're talking about are simple TCP streams. So streams, how TCP actually works. We're just going to see that first without any issues. In exercise 2, we look at retransmission of packets. Okay, so there's again noise that's introduced into the system. Okay. So here again, this is your intro to TCP. Again, if you want to just take a look a little bit about TCP, how it's a dominant transport, it's an overview. It explains what we already kind of know, but if you want to kind of read it again just to get an idea, this is your TCP header. Okay, and we're looking through most of the stuff we did. I know, sorry about this. It's not a straight line. I tried my best. So these are all the details of TCP. I suggest you read through just for to remind yourself. Okay, check some field for corrupt packets, right? If there's any errors or lost packets, that's there. So anyway, this configuration section tells you how each of the traces, okay, these captures were generated. Okay, so I suggest that you read through, but we have traces on a private network, okay, and then one over internet, okay. So there's it show the setup here. This just shows part B with no noise, but this is the setup that's being done. So it's okay. Traces in this exercise were taken on a private network, okay. A desktop PC, okay, which is shown in the image here, is connected to a laptop via a cable modem router. So this is a router that's also a cable modem. On both machines, we installed a tool for generating TCP streams. Okay, so this is TCP streams were generated. They generated them. That's not important. With the specific characteristics called TTCP, we actually use PCA TTCP, PCAT TCP, a version of TTCP for Windows. Okay, whatever. This is just the way the packets were generated. You start a receiver on one machine and then a transmitter on the other. Transmitter establishes a TCP connection with the waiting receiver and then sends data over an open channel. Okay, so the data is captured, you see. So this is the client and this is the server, right? The PCA. Here we have a client and we have a server, and then the file, the capture that was done is the TCP using PCA TTCP underscore N1 capture. That's what this one is. Okay, and then in another section, we're going to talk about the. So here's the setup, right? Okay. In part A and part B, there's actually another one here. There's a TCP connection between the desktop and an external server. That's another setup here as well. Okay. So part A is this remote connection. Okay, and then we have a local connection. Okay, so there's two TCP connections. Okay, and this first experiment is on a quiet network. Okay, so there's no noise introduced, so we're not expecting any retransmission, no lost packets or anything like that. Okay, so this is sort of how the setup was done, but basically how the traces were generated for TCP, PCA, TTCP, N1 capture, which is shown here between the laptop and the desktop. Okay, laptop is at 192.168.0.102. Okay, and that's actually shown right in the image here. I actually redrew this for you. Okay, just so that it's a little clear what's going on, because it can be a little wordy. And then, so that's how this was generated. So when you see this file, that's the connection. The first message, we're going to look at TCP, the handshake, because TCP generates a handshake with a SYN packet. We'll see this in our in the setup here. This shows you what you're going to see. We're actually going to open this up and take a look at it. Actually, why don't we open up wireshark right now? Okay. So what we're going to do is we're going to open up wireshark. Okay, let's go through this this document here. So the first thing we want to do in exercise 1 part A, okay, what we're going to be using is we're going to open up the file TCP SSH cap, okay, and it says depict the sketch or sketch the network diagram of visible nodes and associated information. Follow the text of the lab in the associated PDF to answer these questions. IP address started with 192 is typically the address of a private class C, that's the local connection. Internet communication between two end nodes typically involved a router in between. Packet is captured on a particular IP interface. The IP and MAC address of all the nodes may not be available in the captured file. Okay, to make things simple, like I said, I'm giving you the diagram of the entire network. Okay, just to make things simpler. So we have different parts of this connection. If we look here, part A, exercise 1 part A, is the connection between the desktop that's in the local network and a remote server. Okay, and it's going to be an SSH connection over TCP. Okay, so in order to open that, we need this TCP underscore SSH.cap. We're going to go and we're going to File, say Open, and then we have to, I downloaded all the files from Econestoga, TCP SSH cap. Say Open. Okay. So now we've downloaded this was captured already and the experiment was already done. So this is what was gathered. Now, Wireshark is on one of these nodes. We don't know which one. Okay, but you can kind of guess. You probably can guess. Can't be here on the server because MAC is unknown, right? Okay, this is part B, so let's go first to here. All right, so we got TCP SSH cap downloaded. We downloaded this file and we opened it in Wireshark. So it says here, identify the nodes that are involved in the TCP IP MAC communication with the remote server. Okay, TCP SSH, that's what we did. Identifications are IP address, MAC address, port ID. You record as much info as you can find in the file, and you may add port, IP, and MAC addresses directly to the figure drawn in number 2 below. Now I kind of answered this one for you. Okay, so just you can redraw this one if you like, but the idea is that where was the TCP SSH capture file completed? Okay, in TCP SSH cap. Okay, actually I didn't draw it for you. Within the file here, you're going to see. Let's go through here. So 128.153.4.131, right? Okay, 192. Where's 128? 128.4. Okay, this looks like, and I kind of already started this for you. You've got this guy, you got the router, and you got this guy. Okay, and just basically redraw this for now. Then the next question is, where was Wireshark installed? Right, where the Wireshark file, right here. Where in the network was the Wireshark file captured? Okay, now the hint is that you don't know the MAC address of the server. Okay, now where is all this information coming from? This information and this information and anything in the cable. The cable, you want to know what is you want to include the cable modem in your diagram. What is its IP or MAC address, and can you know that? Okay, from this connection. So where you're going to get all this information is you're going to look over here, okay, in these packets. So 192.168.0.101, you can find out its MAC address. It's right here. Okay, and we have it. We have it 00, so 0007 E9, etc. is right there. Okay, and then the destination. Now you know. Okay, this is the destination is always the router, right? So 000625 is your router. Okay, so but we don't really have. Do we have the IP address of the router in here? Well, it's always going to be 1. Okay, so you can know the IP address of the router. Usually it's 192.168.0.1. Okay, so you can know the IP address in this diagram. Just draw this connection, including the IP address of the router. Okay, so that gets us going a little bit. All right. So determine where in the network. Okay, explain why you think it was captured there. Well, because we don't know. We don't know the what? We don't know the MAC address of the remote computer because we're not on that network. Okay, so that's the idea. Okay, these 3 questions are not in the PDF. Start the questions here. The details start on page 11. So in case you're reading through the PDF as well with me. All right, now part B. What's part B? Part B is now we're looking at, okay, for this we need, for these questions, we're going to use TCP SSH cap. Okay, we're going to use this connection to answer some of the questions, and we're also going to use TCP PCA TTCP, which is this capture between these two, between the desktop and the laptop. Okay, so let's start with the first question. Which packets contain the 3-way handshake? Well, they're the SYN and the SYNAC, right? So SYN is the first one. Okay, so who was making the connection? SYN. Who made this question? So the source was 192.168.0.101. That's the desktop PC, right? So this guy initiated the connection. SYNAC. Okay, so SYN comes from, this one comes from 128.153.4.131. That's the server. Okay, and the destination is my or the desktop PC. Okay, and this is an SSH connection. And there's an ACK because this guy's acknowledging the first packet, right? And then the third message in the 3-way handshake, okay, comes from the desktop computer back to the server to acknowledge the SYN from the server. Okay, so these 3 packets are part of the 3-way handshake. Okay. All right, number 2. What is the actual initial sequence number in each direction in the TCP SSH cap? And how did you determine this? What's the initial sequence number? So what we need to do, I'm going to make this a little smaller here. Let's go in here. It's okay. Okay, we're looking at TCP because we're not on the IP layer, we're not on the Ethernet layer, we're on the TCP layer. What's the sequence number? Okay, well, look, the sequence number here, okay, the first packet, right, for 192, for 101 here, okay, to 128.153.4.131, it says sequence number is 0, but this is a relative sequence number. So if you want to know the actual sequence number, okay, what you have to do is go in. It's right here, raw. You can look at it there, or what you can do is you can get. You see when I click on this, it highlights right here C6A14E5A. That's the hex value, the absolute value, right, of the sequence number. So that's the number of the sequence number for that packet. Okay, so that's from 101 to the server, from the desktop PC to the server. So the server is going to expect one more. So the next one is going to be, look, so this one, so 192.168.101 to the server. If I look not at the second packet because that's going the other way, if I look at the third packet, you see sequence number is 1. So relative sequence number is 1 bigger than that first one. 5A 2 ends in 5B. You see that? Okay, and relative is just relative to the very first packet. So wireshark is keeping track. Okay, and the same thing. If you look at the second packet from 131 to 101, that has a relative of 0. But now if I look from the next message from 131 to 101 is this fourth message. This one has a sequence number of 1. So you see, it always increments. The next message is one more than the one that came before. So that's how this works. All right. Question 3. Use the SYN and SYN-ACK packets in both traces to compute the round-trip time for each connection. How does the round-trip time for a machine in the local network compare to the round-trip time in a remote server? Well, you would expect that it's going to be less in a local network. It doesn't have to go as far. So let's look. What we have to do in order to determine. So look, the TCP connection from between the server and the desktop is the remote connection. The local connection is between the laptop and the desktop. Okay, so TCP SSH cap. Let's find first what is in TCP SSH cap. What is the time of capture of the first packet? Okay, so this one right here is 0, right? And then so that's from the source to the destination. That's when the first message was sent. The second message, which is the reply from the server, assuming that let's remove processing time, okay? So the first to second message is at 0.049886. That's 49 milliseconds after. So we're looking at a round trip time of 49 minus 49.8, 49.9 milliseconds. Okay, so that's the remote connection. Now they're asking, look, round trip for each connection, right? How does it on the local network? So this is the remote network. Now in order to get the local network, I got to go and I got to get TCP PCA TTCP.N1 cap. So we'll go in here, say open, and now we need this guy right here. That's our local one. Say open. Now we got this one. Okay, so now let's look. We're looking for SYN-ACK, right? Because there's going to be a connection between these two guys. So what we need, let me go here and see if I can open it a little bit more. All right, here is SYN, here is SYN-ACK, and this is ACK. So these are our three-way handshake. Okay, 1, 2, 3. Okay, so let's take a look. Now the second one, the first to second message, right? SYN to SYN-ACK. This one is at 0.02936, and then this one is the response is at 0.005476. So what's 0.5476 minus 0.005476 minus 0.02936? I get 2.54 milliseconds when you take these two. Okay, so round trip, the comparison from 49.9 to 2.54, it's as expected, right? It's going to be a lot. The remote connection is going to have a longer round trip time. Okay. All right. Now we got to go in TCP PCA. Okay, N1 cap. Which of the packets contain only header and no data? Header with no data. Okay, so so this is a little bit tricky because it requires to write a filter. Okay, so you write a display filter to isolate these packets. So look, which of the packets contain only a header and no data? Well, what that means is the TCP length is 0. Okay, so if I go in here, the way you write this, I know it's a little bit tricky. So you type TCP.len. This is a filter. Equals 0. Okay, and when I type that, these TCP packets have no data. Okay, their length is 0. Okay, and that's what we're looking for. See TCP segment len equals 0. Okay, so these are the ones. This is how you write. So look, we're looking at TCP, so the TCP component, and then the len component, the length component. Okay, that's just how you write it. Okay. So how many packets in here have, and again we're in TCP PCA and 1 cap. How many packets, okay, have a length. Let me move this over a little bit. Okay, how many packets match this filter? Okay, so we have how many packets contain only a header and no data in this one. So what do we have? We have 1, 2, 3, 4, 5, 6, 7. I see 8 here. Okay, unless I missed something. Okay, and okay, now the next part of the question is, okay, right, a display filter. We did that. How many packets match this filter in the in TCP as SSH cap? So what I need to do, I'm going to copy this guy. Okay, and I'm going to go in here, go into open, go in this guy right here. This is the local one. And then what we're going to do is, oh, it's already there, stayed there. Okay, so how many packets match match this? What you could do, instead of counting it all, if it's a long number, just highlight everything. Okay, and when you highlight everything, it tells you, or I can even just look right here. Okay. Okay, the number of it says 53 that are displayed. Okay, so there are 53 packets in the local with this with no, where the length is 0. Okay. Look at the bottom. Oh yeah, we can see, like I said, look down here, and you can see how many packets have this length. Okay. The next part is to look at. Let me see here. Okay. In the next part, we have it says, what is the only segment in a TCP stream without the ACK bit set? What is the only segment? Well, if we look here, whenever we have the SYN, where's SYN? Here, right here. You see SYN? This is the only one without ACK. If you look at all the other ones, they all have an acknowledgement, right? Because that first one is not acknowledging anything. Okay, so that's how that one works. Okay. It says ACK bit set. Okay. So what you could do, actually, you can actually use a filter. So you could say TCP dot ACK equals 0. Okay, that's how you would write a filter for this to get this bit. Okay, so you can actually write this filter and see that the ACK bit is 0. So let me see right here. This is what I'm looking for. Okay, this ACK bit is 0 or not set. You can, so if I say TCP dot ACK, now I could say equals 0, and that just gives me this one packet. Okay. All right. Anyway, that's how you set a filter for this. All right. The next question in TCP PCA to TCP.N1 cap, do all of the followings? Okay. Wait a minute. Am I in? Which one do I have here now? Just make sure. This is SSH. So I got to go back and say open. This guy right here. Say open. Okay, that's back. I don't need the ACK filter set. All right. So that's gonna clear it. Okay. So do all of the packets from the server to the client contain the same acknowledgement number? Why or why not? So the acknowledgement number, if we look, okay, we look for, okay, we just want TCP. Okay, and is the acknowledgement number the same from the server to the client? Well, the server is the laptop, the client is the desktop in this case. Okay, so just so you don't get confused by this question, do they contain the same acknowledgement number? Okay, so the server is the 102, the client 100, so we're going to go here, 102 to 100. What's the acknowledgement number? It's 1. Okay, 102 to 100. What's the acknowledgement number? 2921. So answer is no, right? Because what does the acknowledgement number do? What does the acknowledgement number do? Right? The acknowledgement number acknowledges it's basically saying I acknowledge all the sequence numbers up to this point. Right? So it's saying basically the acknowledgement number is the sequence number that it expects next, okay, from the other side. of the connection. So that's why it's not the same, because it's the packets are increasing, right? The numbers of each packets. Do all the packets from the client to the server have the same acknowledgement number? Okay. From the client to the server, do they have the same acknowledgement? So client is 100 and 102. So from 100 to 102, what's my acknowledgement number? 0. Okay, that's the next. So 100 to 102. What's the next one? 100 to 102. Okay. Where's the acknowledgement number? Is 1. Okay. 100 to 102. I did that one. 100 to 102. Acknowledgement number is 1. 100 to 102. 1. 100 to 102. 1. 100 to 102. 1. Okay? Hasn't changed. Why? Well, the client, right, doesn't receive anything from the server. The client is sending, if you read the document, the client is sending data to the server, but it's not receiving anything from the server. Okay? So the acknowledgement number is the same because this, the server is not sending it anything. Okay? So the client doesn't receive any TCP segments that contain data. Okay, so to answer, let's see, number 7 here. In TCP, PCA, TTCP, and 1CAP, how many packets does packet 12 acknowledge? And then how many packets does packet 14 acknowledge? Okay, in order to answer this is a little bit tricky. What you need to do is go in and look at the acknowledgement numbers. Okay, so if we look at 12, okay, what we need to do is we need to look at a number of packets. Okay, so if we start at 12, so what we are interested for 12 is from 102 to 100, and even for 14, right, is from 102 to 100, and that's what we care about. Okay, so if we look at 12, okay, what is the acknowledgement number for 12? The acknowledgement number for 12 is, let's see here, for 12 is right here. This is the relative ACK number. This is what we care about, okay? 5841. Okay, so if you make a chart, okay, and what you want to do is you want to say, okay, packet 12 acknowledges up to 5841. Okay, so 12, 5841. Now we got to look at what came before that. And did anything acknowledge anything that came before that? Okay, so what we're going to do is we're going to say, okay, 12 acknowledges 5841. Anything, we're going to look at now we're going to go back. So from 102 to 100, that's the ones we care about. So the next one, what does packet 8 do? Well, it acknowledges up to 2921. Okay, so 8 acknowledges up to 2921. What packets were sent in between? Well, the packets that were sent from the other side, right? Because 102 acknowledges 100. So the packets that are in between are these guys. You see? Right here. 100 to 102. So this one has a sequence number of what? So we got to look at 9. Okay, 9 has a sequence number, okay, of 2921. 10 has a sequence number of what? What does it have? Of 5841. And then 11 has a sequence number of 5841. Okay? So now look. Basically, this guy acknowledged up to, right? The acknowledged 2921. What was the last one? This is 2921. So this guy acknowledged everything up to this this frame. Okay, so now we're up to date. Then you got 3 frames came in. This guy acknowledged where is it here? Up to 5841, and that's this last packet 5841. So it's acknowledging 1, 2, 3 packets. Okay, so it's really simple. You just gotta kind of tease it out a little bit to kind of understand what's going on. Okay, but if you make a chart, it's actually easier to understand. Okay, so in this part, we're going to answer. This is the setup. We've got noise in between from the desktop to the laptop. Okay, how many TCP segments are set from port 4481 on the desktop to port 5001 on the laptop machine? So what we need is we need this guy right here. Okay, this is the transmit. Okay, retrans T is transmit. So what we need to do is go in, open. Now we need this is transmit. This is receive. So transmitted. Say open. Okay. So how many TCP segments were set from port 4480? Okay, on the desktop to port 5001, and basically they want us to write a display filter to isolate this side of the connection and use it to answer questions for. You need the same display filter on both sides. Okay, so we have the receiver and the transmitter. Okay, so you can use this hint here. Use the summary option and analyze. Okay, so basically, you can. I'm going to show you how to write the filter just to save some stress. So TCP. Now, in order to write the filter, we need to isolate a port. So port equals 4480. So we're looking at all the packets, and then okay, TCP dot port equals 5001, and okay, what we care about is the source port, right? We want to. I'm isolating the source, so it's IP dot src, and so it's from the desktop machine, right? So sent from on the desktop. So we got to put the desktop machine. If you look in the image, is 192.168.0.100. Push enter, and these are all the packets that were sent. If we look here, we've got all the packets that meet this filter. Okay. Okay. So if we look, if we look at on the transfer side. Okay, we should see that there are of all the packets that were captured, 48 of them were sent from the desktop to the laptop. So 48 of them were sent that way, and if we want to go the other way, okay, if we want to go the other way, we have to basically use the other file. Same filter. I'm just going to copy just in case it doesn't get kept. So now we want to go retrans R. So we open, retrans R, open, and now we have the same filter. It stayed. So now how many were received on the other side is 43. Okay, so we have a discrepancy here, right? One side transmitted 48, and only 43 were received by the other side, wireshark. So what do you think happened? There's noise in the middle, right? So we got to figure out what happened, right? So the answers found in this question 1 should not match. Why? Why they should not match? Well, okay, let's go in and see. Well, they don't match because packets are lost, right? That's one. So 5 segments ended up getting lost, right? Because of that noise. And if you look, there's 9 retransmissions. So you see, look, that doesn't mean that 9 packets were lost. It means some of the retransmissions might have been lost. So here is here's a fast retransmission, fast retransmission, fast retransmission. This means that we have these. There was lost packets basically. Okay, so that's good. So now the next question is examine the suspected retransmissions that are identified by Wireshark in both retrans R and retrans T. Okay, So what we care about here is another filter. We're going to say TCP.analysis retransmission. That'll get rid of, that'll take in only the retransmissions. Okay, so I kind of give this to you. The filter is TCP. Look, I'm just gonna grab the transmission. I give you the filter TCP dot retransmission. Okay. Oh, sorry, TCP. It's analysis. It's a subset of the analysis. Now, see how it kind of gives it to you? Analysis dot, and then here we can say, we can look for retransmission if we want. It should be there. Retransmission. Okay, and then we say that's the one we want for both sides. So, how many are on each side now, right? Because that's one thing we want to know, right? We want to know on the transmit side and on the receive side, and then we want to compare them. Okay, because that's what they're asking. They're saying, identify all the packets. Oh no, sorry, that are retransmission, and you can copy, print screen and show. Use the filter. Are they the same? Are they the same packets identified in both traces? Okay, so let's see. Let's take this guy. So what you can do for this is just copy. So look, I've got how many here? 9. Okay, in R, and then I could also open up another. Let me open up another wireshark. Open up another wireshark for comparison. So this is retrans R. If I go in here, go open, and now I need T, right? Retrans T, say open, and then take the same filter, right? And go here, paste that filter, push enter, and now we can compare, okay? We can compare the two. There are 9 in both, right? There are 9 packets, but look, 12 is from 0 to 100, sorry, 100 to 102, right? 100 to 102. We have 168, 100 to 102. We have, most of them are the same. The time, there's going to be a difference in the time, right? Because there's a propagation delay. The last one is 100 to 102, 15, 14. So they're the same on both sides. The retransmissions are the same on both sides. You can also look at the sequence number, which is another thing you can look at if you want to compare this sequence number with this sequence number. So if we go in 2001 and 2001, okay, so our next sequence number is 2001. So they're both, it's the same packet right here. Okay, so you can look at, or you can actually look at the exact sequence number is 1001, 1001. Okay, so you can look at either. They're the same packet that were sent from the others. So these retransmissions were not lost, is the idea. Okay, so if we go down to question, so we did this one. How do you know the packets are the exact same? Yeah, they're the same. 4. Identify all of the packets in retrans T up to packet number 24, and for each segment that's lost, identify the retransmitted packets. So this is a duplicate acknowledgement. So this guy right here is a fast retransmission because of it received. So there's a duplicate acknowledgement, and then a fast retransmission is going to be sent as a result. Okay. So what we're looking for is duplicate acknowledgement. Okay. So you see in this packet right here, duplicate acknowledgement, duplicate acknowledgement, duplicate acknowledgement. Okay. So 9. Okay. 11. Okay, 13 are duplicate acknowledgments. Is there anything else that's a duplicate acknowledgement? 17 is a duplicate acknowledgement from 102 to 100. And we have, because they're asking up to 24, right? Up to packet number 24. Duplicate acknowledgement at 19. Okay, 17, 19. And again, there's a fast retransmission in response to that. And up to 24 is what we care about. Okay, there's one at 25. So which ones are the duplicate acts? They're asking us, what are they asking? They're saying when the receiver identify all the packets up to packet 24. For each segment that is lost, identify the retransmitted packets. So this guy is a duplicate acknowledgement. Okay, so whenever there's a duplicate acknowledgement from 102 to 100, what are you going to get? You're going to get a fast retransmission due to that. Okay, so let's take a look at the first one. So if we look at number 9, let's go to number 9. There's a duplicate acknowledgement, right? So number 9 has a duplicate acknowledgement, and so 9, 11, and 13 are duplicate ACKs. Okay, where's packet 6? Packet 6 sent the first acknowledgement. Okay, so this one here sent the acknowledgement number was 1001. Okay, packet 5 actually sent one too, 1001. Okay, so this one acknowledged up to 1001. Okay. Now, what happened after that? If you go down to where's the fast retransmission, because you're getting duplicate ACKs here. This fast retransmission, what's it for? This fast retransmission is for 101. Okay, so this fast retransmission is in response to the duplicate acknowledgement. That's a duplicate for packet number 6. So you see TCP duplicate acknowledgement from number 6. That's what this guy's giving us. We look at number 6. The acknowledgement is 1001, right? So we got it. The same one here as number 6. This is another one, a duplicate acknowledgement that's the same as number 6. See, the acknowledgement number is 1001. So then what happens? You get a fast retransmission with 1001 as the number. Okay, and that's in packet number 12. Okay. If we look at other ones, let's look at this one right here. This is another duplicate acknowledgement that happened for number 6, but it doesn't matter because we already sent it and nothing was lost. So it's this one is okay. Let's take a look at the other duplicate ACKs. So we have a duplicate ACK here for number 16. So 16. What's the sequence number? The relative sequence number is 1. Okay. Acknowledgement. It's acknowledging up to 2001. But anyway, this guy is what's the acknowledgement? 2001. Okay. So here it's got 2001. 16 is 2001. Now they're saying this is another time that I received the same 2001 acknowledgement number. Okay. Then here I get it again. I get 2001 again. So now I had 2 duplicate ACKs. Now I'm going to have a fast retransmission with the sequence number of 2001. Okay? So 17 and 19 are duplicate ACKs, and then the fast retransmission happens in packet number 20. Okay? So anyway, that's what's happening there. Okay. There's a little bit more. You might want to analyze a little bit more, but I'm going to stop here. Okay. The next one. When the receiver sends a TCP segment to acknowledge data received, even if it's only a TCP header, the segment can also be lost, right? Basically the ACK can be lost, right? Are there any such losses in retrans T or retrans R? That's the question. Is there anything that is like that? And well, if you look at if you type this filter here, if you have both of them, I have to open up. Okay, retrans T. I'm going to go. This one's going to be retrans R. Okay. Filter is basically what we need for both of them is TCP analysis. Okay. And then here, dot ACK, and it's already telling us, right? ACKs frame. This is the one we want. Okay, the frame, and okay, we want IP dot source 192.168.0.102, right? We're looking for, because the acknowledgements are coming from 102. Push enter. Okay, so that's in the transmitted. These are from the transmitter. And then here we're going to do the same thing. Receives. These are the packets on the receive side. And what we're going to do is we're going to take a look and see if any of these retransmissions were lost. If the numbers are the same, okay, so here I have 19 packets are retransmissions on one side, and then here we have 19 packets that are received. So these retransmissions, okay, these not retransmissions, these acknowledgements, no acknowledgement was lost on both sides, because the wireshark on one computer is getting the same thing as on the other computer. So there's no losses here as a result of this. Okay, so let's take a look at the last two questions in the lab here. And what it is here, what we're seeing is we've got this an HTTP connection over TCP that's made between our desktop and another server. It's not this port, not this IP address, but another server. And I'll show you what that is. And the file is not TCP SSH, it's now TCP HTTP. So we're going to go in. That's what this one is, right? Capture file. So what we need to do in order to do that is to open and go to the TCP capture file and grab that. And what it says here is page 24 shows you how this file was captured, and I already explained it. It's an HTTP server connected with our desktop. So let's just take a look. I'm going to show you here what is that server and what is that connection. So these first three packets, if you read the text here, it tells you that this is the three-way handshake: SYN, SYNAC, and ACK. And we saw this three-way handshake done before. Okay, and we can see that the server that we're connecting to, so we're connecting from 101 here, okay, to mail-b.isi.edu, okay, and it has, if we look down here, you can see its IP address is 128.9.160.27, okay. However, we don't know its MAC address. Because why? Because we're on a different LAN than the server, right? So we won't know still, just like we saw before with this TCP SSH, we don't know its MAC address because we're not on the same on the same LAN network. So what is this? So look, this is the Ethernet layer. What is this MAC address? And we learned in a previous lab that this MAC address is that of the modem, right? The modem router, the router basically, right? Because the IP address at the IP layer is outside of our local network. So when we do the ARP, okay, it's basically going to, well, we're going to go to our routing protocol. It's going to say, okay, this is outside of our network. It says, okay, give me the IP address of the router, and then you're going to get from the IP address of the router. Now you want to send it on the physical network. This is the MAC address of the router. Okay, so to be clear, Wireshark is installed on the desktop PC, and that's what's shown in here. The other discussion that they have, just as a side note, selective acknowledgement. So I'll just show you here. In the SYN packet, and they describe it in the text. In the SYN packet, when you look at the TCP, it says that the client has selective acknowledgement. And remember, selective acknowledgement allows you to select the packets that are missing, and then just request those. So the client says, if you look at in the options here, okay, they show this discussion. It says that the client has selective acknowledgement permitted. Okay. However, the server, when you look at the options, it doesn't have it. Okay, so the client says I allow for selective acknowledgement, the desktop here, but the server does not. So there's no selective acknowledgement in this connection. Okay, selective acknowledgement is not going to happen. So anyway. Now what we're going to do is we're going to analyze something that happened here, okay, at packets 15, 16, and 17. And the discussion here is that they say that packet 17 is marked as a suspected retransmission, okay? It's marked as, but actually, if you look now with the latest version of wireshark, it actually tells you something else. It tells you out of order. Okay, so what's the point here? The point is this. TCP has the ability to reorder packets based on their sequence number before they're sent up to the application layer. Okay, so any out of order packets get resequenced before they get sent up. And so here, what I'm going to show you is that you can see this in action. That you have this packet 17. Okay, this is what the discussion says. Packet 17 has a sequence number of 8761. Okay, but look at the packet that came before. Okay, from the server to the client, not this guy. This guy is from the client back to the server. We care about this one. Okay, this is messages from the server, right? Packet 15. Look at its sequence number. It's bigger, so it's 10221. Is bigger than 8761. So what's happening here is this a retransmission or not? Well, okay. I'm going to tell you that it's not a retransmission. Packet 17 was sent by the server to the client before packet 15. Okay? Why? How do I know that? One piece of evidence is the sequence number is lower. Okay? And that could be a retransmission, right? Because the sequence number is lower, it didn't get it, it's retransmitting. That's one possibility. But if we want to get an idea of whether or not it's a retransmission or if it's an out of order packet because packet 17 may have taken a longer route, what we're going to do is we're going to look at the messages that came from the server to the client. Okay, so 15, what's the differential, the time differential between 17 and 15? Well, that's 3.523242 minus 3.521826. Okay, and I'm going to bring this into the picture here. Okay, so this is a picture that I drew. And so that is 17 minus 15, 1.416 milliseconds. This guy minus this guy. Okay? 1.416 milliseconds. Now let's look at the next message that comes from the server to the client. Well, that's 19. Okay, and by the way, this hint is here in the question. Okay? 15, 17, and 19. Okay, so now we got to look at the time differential between 19 and 17. Okay, so that's like basically the sort of round trip time from the server to the client. Okay, and then we're going to compare them. So now we're going to look between 17 and 19. So if we do that, 19, look at 19. That's a 3.549150. Okay, so that minus 3.523242 at 17, and that is 25.77 milliseconds. So this is much larger than this. Okay, so this is much larger than this. If it was a retransmission, you'd have to wait to know that there's a problem. You need to wait at least the round trip time to know that there's a problem, right? But it didn't happen that way. What happened is this delay here between 17 and 15 is much smaller than the round trip time. So what's more likely is that packet 17 was delayed. It took a different route than packet 15, and so it needs to be reordered. So what happens is it's an out of order packet that then needs to be placed in basically 17 needs to be placed before 15 before it's sent up to the application layer. Okay, so that's what's happening here. This is in action what's happening with TCP and how TCP can reorder the packets. All right, that's it for this lab. I hope you enjoyed the experience, and we'll see you next time in class.